Hello again. Tonight we're going to do a comparison between the planets Uranus and Neptune in our solar system. This was something that a Broward Astronomy member had suggested. I had been getting off astronomy topic a bit too much, so this kind of draws things back to what people might have come here to look for. These are two planets in our solar system. Uranus was discovered in 1781 by Herschel, and Neptune was it's kind of up for debate, but the first person to write down that he observed it was Johann Gallic, and then two other guys were also added to the list that also observed it in the same time frame. I think it was in the same year. It's a question of which saw it first, but they all get sort of co-discover. Neither is directly visible by naked eye, except it may be a very dark sight if your vision is already dark adjusted. Typically, you'll need something to magnify it a bit. Both of them are actually bright, but they're very, very far away in our solar system, so they're pinpoint sized targets. You can see them basically as just spots in the sky with a 7x or greater binoculars, not with a wide field of view. So if you have like 735 or 750, you can see that it's a spot in the sky and they have two different colors, and they're not the usual white or red that you would see of a star, and they don't twinkle, so you can tell they're planets. But the best way to see it if you're an amateur is to have a telescope with a narrow field of view, longer focal length, and with a short focal length eyepiece to give you more magnification. Since they're relatively bright for what they are, don't focus so much on the aperture, the light gathering of it, unless you're taking really detailed pictures of it. If you just want to see that it's round and has color, one of those inexpensive, like F14 refractor telescopes, if you can get it pointed to the target, would be fine. So comparing them with Earth, Earth is one astronomical unit from the sun, 93 million miles roughly. Uranus is 19 astronomical units, so 19 times that. And Neptune is 30 times that. So getting way out into our solar system, not before not to the Kuiper belt out where Pluto is, but out towards the outer edge. Both of them are spherical. They're large enough to be hydrostatic equilibrium crushed into spheres. They have very large, dense atmospheres, and the atmosphere starts out very tenuous and then gets denser and denser. And if you measure the volume, including the atmosphere, then Uranus is about 63 times the size of the Earth, and Neptune is about 58 times the size of the Earth. But unless you're looking at them side by side, you don't really see that one is any significantly larger than the other. For a long time, they've both been referred to as gas giants because we see no terrestrial surface on them. Their outer atmospheres are lower pressure, hydrogen, helium, and methane. And then as their size allows the gas to press down tighter, you find that the lower parts of the atmosphere are either gases or ices of ammonia, methane, and water. Neither planet has a terrestrial or rocky surface, but way down below the lower, denser atmosphere, they have rocky cores. And the core volume of Uranus is about 8 times the size of Earth. And for whatever reason, the rocky core of Neptune is quite a bit smaller than Uranus is, even though the outer planet size is roughly the same size, but it's slightly smaller than the terrestrial diameter of Earth. So comparing the two of them, how about the year? How long it takes for them to go around the sun? Uranus is about 84 years. Neptune, being like the next step farther out, is 165 years. Still far shorter than Pluto, but Pluto's a dwarf planet. Rotationally, they're somewhat slower than Earth. Uranus's day is about 0.72 days. Neptune is about 0.673 days. Their orbital inclination, if you take their entire orbit and judge it as how tilted is that to the plane of the solar system, small amount. Uranus is 0.78 degrees, Neptune is 1.78 degrees. Where you see the big difference is in the polar axial tilt. If you think of it as a sphere spinning and it has an axis going up through the center of it, and you tilt it over, Uranus has kind of been knocked on its side. It's almost 90 degrees tilted over, whereas Neptune is kind of in the same ballpark as Earth. Earth is 23 degrees and Neptune is 28 degrees, which gives the planets seasons, sun angle on planet atmosphere. But Uranus it's kind of like tipped on its side. And so one pole tends to get more light than the other. The number of satellites, Earth only has one, the moon. Uranus, as of last year, has a confirmed natural satellite or moon count of 29. Neptune has 16, and that 16 was a little lower a couple of years ago for Neptune, but we've done some observing with the James Webb Space Telescope and found a couple of more moons. The average temperature, now where you measure the temperature at what altitude becomes important. The troposphere, where the pressure is roughly where the tropospheric pressure is on Earth, 1 bar of atmospheric pressure. Uranus is negative 220 degrees Celsius or minus 364 degrees Fahrenheit. And Neptune is negative 201 degrees Celsius or 330 degrees below zero Fahrenheit. Why there's such a distinction between the two when their atmospheres are so similar has to do with what's cooking down below. Heat in, heat out kind of thing. Atmospheric thickness. So there's a lot of information that you can gather as to why they would be 19 degrees Celsius difference between the two. Magnetic fields, they both have magnetic fields, so they both have aurora. But the interesting thing is, with Uranus kind of tipped on its side, its aurora being at its poles means it kind of looks like the aurora is at its equator, not at the poles. And in the case of Neptune, the magnetic field energy levels are such that you don't see the aurora in visible light as much as you see it in ultraviolet light. So it's kind of like Mars in that Mars doesn't have much in the way of a magnetic field, but it does have an aurora. You just can't see it in visible light. It's in UV, which is invisible to the human eye. As to does it have orbital debris fields like rings or ringlets or ring arcs or whatever they want to call them these days? Yes, it does. The particular rings are much like the magnetic fields and the aurora. The density of the rings varies as you go around the planet. So it's almost like there was a moon there, it got smacked into debris, and the debris field got stretched out a little bit, but the rest of the debris is still circling the entire planet. So you get this concept of ringlets or ring arcs because you're only looking in visible wavelengths. But as they look to the non-visible wavelengths like infrared and UV, they're brighter and darker. And so both of them seem to have ring systems, multiple levels of rings, but they're not all visible in the visible light range. Yes, they both have rings.
The other thing about it is that some of the arcs, they might be in resonance one of the moonlets. And so then some areas where the gravity of those moonlets are affecting, those rings are not complete.
Right. You have kind of like what you do with Saturn. You have shepherding moons where a moon's gravity will either push or pull on the debris field, causing collection of debris onto that moon or causing it to push the ring so that like a particular inner or outer ring layer is thinned out by the shepherding moon. What about observations? So obviously the earlier telescopes had to be very large telescopes to get the level of magnification necessary. And the strange thing is Uranus is close enough and bright enough from a dark sky that you can actually see it. And if you track it across the sky, you can see that it's doing one of those loop-de-loops like a planet does, as opposed to a more distant star. Neptune, on the other hand, was so tiny it wasn't easily visible, but they could see perturbations in the orbit of Uranus, which said there's something out there disrupting it. And they actually mathematically calculated where Neptune would be and then looked there and saw Neptune. So Neptune wasn't seen in the sky and then observed with telescopes. Neptune was predicted in the sky and then seen and confirmed with telescopes. So once you can figure out where something is, it tells you where to look. Kind of like that whole Plan 9 thing is, if we see all the perturbations of stuff in the Kuiper belt and we can trace those back and then find the orbital period, we may find that there's something there once we know where to look. At the moment, we don't know where to look. We know there might be something out there, but we don't know where to look. contemporary Earth-based telescopes. Don't look at the newer wide field, survey telescopes, because they're not going to be able to magnify the two pinpoint planets as much. Look to the older, narrower field of view telescopes that can do a large amount of magnification. They're good for looking at the planets in visible light ranges. If you go outside of visible, the Hubble Space Telescope, the HST, it can see in wavelengths of infrared, visible, and UV. It can look at different things. And if you see something at one wavelength, you can use the Hubble to look at it in another wavelength to see if it's something unusual, kind of like seeing the aurora in UV. There are, I won't say deep space telescopes, but there are telescopes that are farther out than the moon in orbit with the Earth around the sun at Lagrange point 2, like the James Webb Space Telescope, which can see in IR. And the two pictures you see down at the bottom, those are taken with the James Webb Space Telescope. The lower left one is Uranus, the one on the right is Neptune. And you can see they both have distinct ring systems that are visible in infrared, and all the little spots you see around the outside, those are moons. Deep space, when Voyager 2 was doing its walk through the solar system, we got some initial pictures from Voyager 2. When New Horizons was on its way out to Pluto, it could take some very distant flyby images, but we have not yet had any orbiters for Uranus or Neptune. However, if the money's there, if they get the improvements for it, sometime in the 2030s, they might launch two different probes. One is called the Uranus Orbiter and Probe, or just UOP for short. And the other one is called Neptune Odyssey, just called Odyssey for short. If they get the funding, if they get created and proven, then they might launch sometime in the 2030s. But given our sluggish, slow propulsion solutions we have available to us at the moment, it might take 10 plus years for them to get out to Uranus and Neptune. Now, why would it take longer than the 10 years it took for New Horizons to get to Pluto? Because if you remember, New Horizons did not go into orbit about Pluto. It did a very fast flyby at about 40,000 miles an hour. So if you want to get into orbit around Uranus or Neptune, or drop something off as the probe would be into the atmosphere of one of the moons, you can't be going so fast that you don't have the propulsion ability with chemical rocket fuel to slow down enough to go into orbit. You can't be going too fast, so it'll take you not 10 years, but maybe 15 years, or their better part of 15 years to get to Uranus and Neptune. But remember, everything starts out with a technical name for a craft or a probe, and then before launch, it gets a commemorative human name. So this is new as of 2024, so reasonably new. The color of Neptune, they've changed their minds. The early Voyager 2 images showed Neptune as being quite a bit bluer than it currently shows. They're not sure whether that was just false coloration or whether it was meant to highlight the atmospheric artifacts of Neptune's atmosphere, like the great dark spot. They don't have anybody precisely they can blame, but they're saying that Neptune should really look more like Uranus because the atmospheric compositions are somewhat the same: helium, hydrogen, methane. However, I can remember being out at Fox Observatory and on a particular evening observing both Uranus and Neptune with my little puny amateur telescope, not even with the Brandon, just with like 150 million Raksutov Cassegrain with a short focal length lens in it. And I do remember Uranus being very, very pale green. And I remember Neptune being blue enough that in the finder's field of view, I could spot it as distinctively different in color than the stars that were in the same field of view. So I remember Neptune not false colored, but visually being blue enough that I could tell it was different than Uranus. But now they're trying to tell us, nope, it should look a lot more like Uranus. Okay, if that's what you say, but I guess I have these lion eyes. Okay, so in summary, Uranus and Neptune, they're both fairly large in our solar system with Earth. They're both farther out from the sun than Earth by a lot. They have atmospheres that are inhospitable to Earth life forms, as far as we know. They both have rocky cores beneath dense, inhospitable atmospheres. We observe them better and better over time with instruments as they get better, ground-based telescopes, then the Hubble, then the Webb. As far as our current propulsion technology, it'll take us billions of dollars and decade plus to get there. Even for just a flyby, it'll take the better part of 2 decades to get there if we don't want to go zipping by it, but we want to go into orbit. Even though we don't have the money yet, they apparently have enough money that the science teams are planning missions to go to both of them, not as flybys, but as the orbiters. But what's the saying? You never know what you're going to find if you keep looking and you keep improving the instruments and where you're going to be looking from, like in orbit. Keep looking. And then links about various stuff. So you can compare Earth and Uranus and Neptune and the distinction of the planetary cores. And I did not know that Neptune's core was smaller than the diameter of the Earth's rocky surface. And then the true color observation. Comments? Questions?
Yes, I have it. One thing that is interesting about when you look at the diameters, not like looking at the volume, Neptune has a larger diameter because it has less gravity to hold the atmosphere close together. That happens with stars too. It's like some stars that like dwarf stars there are more massive. They are smaller than the sometimes the more massive like round dwarfs that sometimes about the size of Jupiter. So because of the gravity just keeps the close together. If you have less gravity to hold together, the planet becomes a little bit larger. And
Yeah.
then the other thing is that if you notice the temperatures
Yes.
of Uranus troposphere are way much colder than the temperatures of Neptune.
Yes.
And this gives an idea that when they form, Neptune formed closer to the sun than Uranus. And we have like what we have Kelvin-Helmholtz cooling. Earth has it. Most of the planets have it. It's the heat that the planet puts out. So in the case of Uranus, the heat that Uranus received from the sun is larger than the output of energy coming out of Uranus. In the case of Neptune, because Neptune formed closer to the sun, it's still like a little bit hotter, and so it emits more heat that it receives from the sun, especially because it's very far away. So the irradiation from the sun looks almost like a regular star if you could see the sky of Neptune. And so that's like the two kind of interesting things about those two planets.
That's
Yes.
interesting. I was just going to ask if their rocky cores are denser than Earth to hold on to so much gas in their atmosphere, but you're saying it's less gravity?
I didn't find density information. All I found was core diameters, and Neptune's was approximated. But yes, Neptune's core is smaller than the diameter of the Earth's rocky surface. So yeah, it has less gravity, and so the atmosphere would tend to swell up a little bit. But if it formed as part of the inner solar system, even though the core is smaller, it would have been hotter. And as it got pushed out to that part of the solar system, it would still have leftover heat. They're actually finding that, I forget which item it was, but there is one of the dwarf planets in the Kuiper Belt that the surface temperature is higher than would be expected for it being out in the Kuiper Belt. And the suspicion is it formed much farther towards the inner solar system, and it got ejected out to where it is in the Kuiper Belt. So it hasn't quite cooled down enough over the millions to billions of years. So that explains why it's warmer than it should be for being all the way out in the Kuiper Belt. So I think that, yeah, I think that Neptune, the rocky core, can be warmer than the original core of Uranus, and therefore Uranus can be colder than Neptune, even though
And then
Neptune's
talking
farther out.
and then talking about the moons, Triton on Neptune rotates the orbits and it's in the wrong
Retrograde.
direction of
Yeah.
retrograde.
Yeah.
And the cool thing is that when they analysis, it's that it might have been a Kuiper Belt body, and it's kind of similar to Pluto in kind of the materials it's made of. So it's a very interesting moon to observe, and then most likely it was a captured Kuiper Belt object.
And
And the Kuiper Belt starts right after Neptune, so that's how we considered the beginning of the Kuiper Belt is that's what we call it, the trans-Neptunian object. So right after Neptune, it starts a Kuiper Belt. And remember, some of the bodies of the Kuiper Belt goes inner orbit of Neptune, just like Pluto. Some other bodies too. So we consider the Kuiper Belt kind of a little bit that inside of the orbit of Neptune in some areas.
Yeah, the orbits of a lot of the Kuiper Belt objects are very elongated and they're off shifted so that sometimes Pluto is actually closer to the sun than Neptune is. So it's inside the orbit of Neptune. And so you can have those sorts of weird orbits when you start throwing things to the outer part of the solar system and they loop around. They don't completely get disconnected from the sun's gravity. They lose a lot of it. So they have a very elongated, like Sedna has a very elongated and tilted orbit, but eventually it winds up going around the sun so that its closest approach to the sun is still out in the Kuiper Belt. It's just a lot closer than at its aphelion when it's farthest out from the sun. So yeah, there's a lot of non-circular, non-flat orbits as you get out to the Kuiper Belt.
Yeah, they describe the Kuiper Belt as being like a donut shape instead of a disc shape.
Right, right. And go out even further and you get to the theoretical Oort cloud, which is supposed to be spherical.
Yeah, so the Oort cloud is about like a light year away from the sun, so it's very far away.
Yes.
But the interesting about the Kuiper Belt is that after the Kuiper Belt, you have the detached bodies. The detached bodies are object from the asteroid belt, from the formation of the solar system, probably even planets around there. Object of the Kuiper Belt, they're in weird orbits far away. That's what we call it, the detached bodies.
Mm-hmm.
Is the gravitational interactions kick those objects even farther away and in even weirder orbits that jumps out of the Kuiper Belt. So it's kind of interesting. And you can consider the middle of the orbit of Pluto being the middle of the Kuiper Belt. So it's like it starts at Neptune and is like from Pluto about the same distance there. So it's a very interesting area.
Yeah, at one point the Kuiper Belt was considered a single belt. Now it's considered three belts, an inner, a middle, and an outer.
Yeah, the Plutinos, the Paulinos, and they all like have weird names that ends with enos.
Yes, they come up with new words with prefixes that differ, and the whole thing is based upon the same root word to keep them all in that diminutive dwarf class as junk out in the outer part of the solar system.
And then two Uranus like has 2-to-1 orbit to Neptune, if I'm mistaken. And then there's like, so they describe those bodies as chemical composition and also resonance to Neptune.
But it's not unusual for astronomers to come up with names for groups of objects that have similar orbits. For example, there are asteroids called Apollos. They're near Earth objects that are all in the orbit with Earth, but not in the orbit with Earth. They have an orbit that still goes around the sun, but their orbit passes through the orbit of Earth. So as long as Earth and that Apollo asteroid don't intersect, everything's fine. but you have to,
No close shave.
how many thousands of
close
years do you have to calculate the probable collision of the two orbits? It's not decades, it's not hundreds of years, it's thousands of years. But there's Apollos, Pallas, there's a number of different names for those similar orbiting asteroids that come into the range of Earth, but they have different orbits, different tilts, different focal points. The sun's always one of the focal points, but there can be other things that are the focal points.
I don't know if you can show in the presentation, if you have to remove the presentation. That is a picture that shows like the beginning of the formation of the solar system with the 4 large planets visible in order, and they were close together, circular orbits, and as the interactions of Jupiter and Saturn made them switch and enlarged the orbit. You have like a really cool picture of the asteroids and the mass of the solar system that caused the late bombardment. It was the change in the orbits with Jupiter, Saturn, and the switch of Uranus and Neptune. That's one of the newspapers pictures, based on the newspaper pictures. It's like a dark picture. Let me see if I can find it.
Yeah, I can remember having seen it. I just don't have at the ready disposal the link to it. But it's theoretical. It's not observed. It's calculations of orbits and
hypothetical. Don't use theory wrong like my students.
Yes, it's postulated. Not even hypothetical. It's postulated based upon available data.
Why are the inner planets all rocky and the outer planets all gas giants? I mean, there's such a huge difference between the two sets of planets. What happens between Mars and Jupiter to make the outer planets completely different?
Well, remember that both Uranus and Neptune do have rocky cores. Jupiter supposedly has a rocky core. Saturn may have just a compressed hydrogen metallic core. We don't quite know that one yet. If you have a planet that's close into a sun and you're forming, it's very likely that that sun is going to be stealing any loose gas. So all you're left with is the heavier stuff, the rocky stuff. As you go farther out, you start with a gaseous planet, and then it gets pushed to the outer part of the solar system. So whatever gas it has, it's big enough that its gravity is going to hang on to it.
So that it's like in the formation of solar systems, you have the vapor line. So the vapor line means that whatever ice is, they're supposed to be ice. It could be water ice or methane ice or whatever, gases you're talking about, they become ice in that line. So that line for us would be half of the asteroid belt. So towards to the sun, those become gases and they are blown away by the solar wind. And always left is the rocky material because it's hot, it's close to the sun. Now, after the vapor line, planets can grow fast, like Jupiter grown like in only a fraction of time that takes for a planet like Earth to form. They form very fast because they gobble up the leftover gases and ices. They clump together, the icy cores, and as they acquire enough mass, they start gobble up the gas and the ices all together. So that's why they grow fast and they have a lot of material. So that's kind of why they're so different, is because there is more material after the vapor line that is not just the gas become ice, and plus the dust, plus the other kind of materials. So they all clump together to make the planet grow big and fast. If you're too close to the star, you only have stuff that is not volatile, like silicates, like metals that end up forming the planet. So that's basic why.
Think of that vapor line as the outer perimeter of the Goldilocks zone.
Yeah. That makes sense.
At least as of what we know today.
Yes, it's always changing.
We may find out that somebody came along with a giant bulldozer and pushed the big planets out there. But we don't have any evidence of that.
My question was always, how do gas giants have enough gravity in their center to attract that much of gas, because the others at least have an explanation, have a rocky core that attracts and has gravity. But gas by itself, to accumulate
Yeah,
a
so
huge
they
amount
start
of gas.
they start about the same way as rocky planets. They start
Oh,
forming like as the gaseous planets start to
mhm.
form, they form with the basic the particles collect to form bolides. But
Yeah.
remember that when you're farther away from the sun, those bolides will not just have silicates and metals, they will have also a lot of ices that make them grow fast. And then as they grow fast, they gobble up the gas. So that's why they end up forming. In the case of Saturn, they think that, like I read in some papers, that it was a collision that stole the core of Saturn. Saturn might have start forming with the core about the size of the Earth, or a little bit bigger, and then it grown, but probably lost its core due to a collision. Now they are not sure if it really has a core. It's like it's the Saturn has such a low density. The density of Saturn is lower than the density of water, so they're trying to understand that. So some of the papers that I read is that Saturn might have lost its core and what I already formed and kept the gas. Now, all the other gas giants, they all have cores about the size of the Earth or larger. But the idea is that they always start in the same way, just that after the vapor line, they have even more material to grow fast and gobble up the gas before the star blows away the gas from the solar wind when it ignites. So if you have an idea, planets, especially planets about the size of Jupiter, Saturn, Uranus, and Neptune, they form even before the star ignites. So when the star is still like a protostar, is when they are forming. Now the smaller planets take some time to form because there's a lot of collisions that make larger planets in inner areas, like before the vapor line.
The other thing to consider is that it's a lot easier for hydrostatic equilibrium to crush a liquefied cold gas or a vaporous gas into something spherical than it is to do the same thing for something that is rocky. There's a
That's
lot
it.
of asteroids and Kuiper Belt objects that are look like peanuts or two potatoes stuck together because they're rocky and they've collided, but they are very loosely holding together with gravity and static electricity. And it will take a lot more material and a lot longer time to crush that rocky material into something spherical. Whereas if it's a liquefied gas that's very cold, or it's an ice, or it's a pressurized gas, that's going to spherize very quickly and more get glommed onto it, as far as we know today.
Let me just send you the picture. I think I found one in a forum that shows kind of the explanation there. So you see here, you can see the colors of the planet. You have Jupiter in green, Saturn in yellow, and Neptune in blue, and Uranus in like cyan. And then the Kuiper Belt was kind of more organized, and there was and then as you see the orbits going changing resonance, you see that Neptune already switched with Uranus, and then you see as those interactions continue, now the Kuiper Belt became very sparse. So that's kind of that's based on the not just the ephemerides of objects, but also temperatures of planets, the composition of asteroids, and so you end up understanding how the Kuiper Belt and the asteroid belt end up forming. This is based on the NICE papers.
This is data that's the result of computer simulations.
Yep.
By the way, even today, we have no space probe that could look at the solar system from above the sun at this field of view.
No.
Yeah, right.
This is calculation of ephemerides of object, how fast they move, and explaining how they fast they move, where they came from. Because the speed of the objects helps us a lot to understand, oh, how you end up being so fast. It's like when you look how Maya looks like a ellipsis, not like this. So it's the result of very energetic collision. So you end up seeing how fast those objects are, which area of the rotation they are, if they are in the plane of the solar system, if there are weird angles, like Pluto has such a weird angle of rotation. And so you end up understanding that if you have some weird rotation and some weird speeds at how they moving, especially they're farther from the sun, is results of collisions. So results of energetic exchange of momentum. So it's like as a planet moves away, the objects that causes, like it comes close and you give like a gravity assist. So that object is going to move faster and that planet is going to move slower. But imagine you have billions of objects doing, as you slow down, you decay the orbit. So that is like like one probe, one asteroid will not change the orbit of Jupiter. But imagine so many asteroids moving close to Jupiter and exchanging momentum. Those objects will be kicked out of the orbit and it's going to slow down Jupiter, even though it's kind of crazy to think about that you could slow down Jupiter.
Think of it as if somebody throws a penny at you, it's like, it doesn't hurt much. If somebody threw a dump truck load of pennies at you, it would hurt.
Yes.
Same sort of thing. You know, you may think of something as, oh, that's so minuscule, that's so small, but there's billions of them. Or maybe collectively that's a lot. Also, these images are top down of the solar system and orbits are not flat. You can see that some of them are a little elongated, but they can also be tilted, as Helen described. So if you had a edge-on view, you would see that not all of these orbits are in the same plane. And if something's close to something else and it has the velocity coming in from above or below, it can actually, without hitting something, affect the orbit of something else to change it to either a more or less elongated orbit or even change the inclination of the orbit.
And then, as you can see, the distance of the planets were less than 20 AU. And then when you see what they are now, it's like close to 40 AU.
Yeah. And 40 AU is not even a light year.
Yeah. So, and the other thing is that if you look at the asteroid belt, there was enough material in the asteroid belt during the first phase that you could make a planet about the size of the Earth. But because of the interactions with Jupiter, that was never able to form. And if you look at the size of Mars compared to Earth, Mars is half of the diameter because it was just the growth of Mars was disrupted by the interactions with Jupiter.
Okay, anything else before I stop recording?